Hi everyone, this is Ayodhya Vijayaratna from Group 19. Today we are discussing assignment 3. I have my team members with me, Giri, Dharar and Nanda. Today we will be discussing Nonsearching algorithm. Artificial intelligence includes problem solving, knowledge, knowledge and reasoning. So out of these three main points, problem solving includes searching algorithms. So basically there are two main searches, which is called uniform search and informed search. In uniform search, also we call uniform search, we also known as blind search or brute force search. There are multiple techniques such as breadth first search, we generally refers as BFS, and depth first search, which is DFS, and uniform cost search, iterative deepening, and bidirectional search. Uniform search does not mention the number of steps needed to reach the current state to the final state. Actually, it will only consider about the cost and the optimized path to reach the destination. When we talk about informed search, it uses heuristic function, which we'll discuss later in this presentation, to reach the goal state that will calculate the optimal cost to reach from destination, reach to destination. Informed search will not traverse search blindly. It will choose the next node to travel based on the evaluation from the heuristic function. So let's discuss BFS first. So in the search method, all nodes will be addressed level by level. When I say level by level, like if we start from node 1 and then if we have 3 or 4 nodes in level 2, we will be first travel to all the nodes in that level before we move to the next level. This technique is used queues. So this that means it's first in, first out technique. This method is not best when all the solutions have a long way to reach. The reason is, in order to find the destination, we have to complete traveling all the nodes or vertex in the one layer. So basically we will be exploring all the nodes. So if it's a lengthy path, if it has multiple layers in depth, so it won't be a good solution to use BFS. And this will take a lot of memory and time to process each search. So there are some applications that we see that BFS is using, such as shared networks, social networking websites, global positioning system, or navigation system. So let's take one small example. This is the same example we have seen in the research paper. So here in the left side, we have a graph. It is a directed graph. That means we have specific directions to go. And also in the right-hand side, we will be seeing the open list and closed list. Open list is nothing but our initial queue, and closed list either contains all the vertex that we already discovered. So let's try to travel through from node 1 to goal state. Let's take a couple of steps. So if we start from node 1, we can clearly see there's 3 directions we could go: node 2, 3, and 4. So once we at the node 1 is already discovered. So we put node 1 to the closed list, and then we will put in the next layer of nodes, which is 2, 3, and 4. So then, since it's a queue, we are using a queue, we will be addressing the first element in the queue, which is node 2. So we will be move forward node 3 and node 4 to the next level of the queue, and then open list start with 3 and 4, and then we will be discovered node 2. When we go to node 2, we have two directions saying node 3 and node 6. So since 3 is already in the queue, we will not be worrying about 3. And then we go to the next level, which is node 6. So we will put node 6 in the queue. and then that time node 2 is already discovered, so we'll see it as in the closed list. The same way we will be traveling, we will be accessing one node at a time from the queue. So next element will be node 4. So that way we will be going from node to discovering node 2, node 3, node 4. Once we discover that entire layer, we will be going to the next layer, which is node 2, from node 2 to node 6. So same way we can continue filling this graph, but I'm not going to go till end because it will take a lot of time. In the depth first search, we called as DFS. It's the other type of the searching algorithm. In previous algorithm, we mentioned that we will be discovering all the nodes in the first level and then move to the next level. The difference between that search and DFS is that when we are doing DFS, we will be going in deep as long as we can go to dead end or reach a final destination. So this follow the stack method, which is like last in first out principle. It also known as the recursive algorithm because we will be going down from all the way down from one node to the end, and then if we not able to reach the goal state, we will be reversing back to the previous step and see the next path. So we may see this search method in applications such as identifying the loops in graphs, or identifying the nodes that are strongly connected to the graph, or finding a solution for a puzzle, which obviously has to have a one solution exist. So let's take one quick example. This is the same example. Instead of doing the BFS, this time we will try DFS. So that case, same way, we start with node 1, and then we will be discovered node 1. And node 1, we will be going to, we have 3 paths to go, node 3, 2, 3, and 4. So we will be seeing that in the stack. Since it is a stack, we will be picking up the last one we inserted. So 4, 3 will be moved to the next level, and node 2 will be discovered. So when we go to node 2, we will have 2 paths again. So 3 is already in the stack, so we will not go this direction, we will go down to node 6. So that's why we see 4, 3, and 6 here, and 2 is discovered by that time. So then at 4 and 3 will still goes to the next step, and node 6 will be discovered because we are doing it in the depth level, not on the horizontal level. So we went 9 to 2, 2 to 6, and 6. From 6, we don't have any path to go. So this is basically a dead end. So that time we discovered 6, but we are not reached the goal state yet. So we go back to the previous layer, and then 2 is already discovered. So we'll go to the node 3. So same way we can fill this graph. So basically what we do here is like node 3, from node 3 we go to node 5, 7, and finally we can reach the destination. So that way we don't even have to discover node 4. So this is very cost effective, and this is useful when we have a memory constraint, or if it's a really deep graph, then this will be a good solution. The next one is uniform cost search, we usually known as UCS. In this search, we expand the nodes with the lowest cost, and also it's implemented based on the priority queue. So when we analyzing the cost, we use the function CM equals CN plus CNM. CM is nothing but cost of the current node, and CN is the cost of the previous node, and CNM refers to the weight of the edge. So if we start with node 1, here we will be seeing some numbers associated with the edges, which we called as weight. So if we start from 1, we have 2 paths to go again, node 5 and node 2. So node 2, we will be seeing the associated cost as 2, which is the cost of the weight of the edge. and node 5 associated cost will be 1. And then after we from this step we will be moving to node 5 now. So node 2 will carry over, and node 5 we will check where we can go from node 5. So we can go to node 9. So when we go to node 9, cost will be 1 plus 1, which is 2. That's why we'll be seeing 9 over 2 here. The same way we will be calculating the cost, and then we will be seeing the shortest path with lowest cost to reach the destination. The next method we call as A star. This algorithm uses both uniform cost search and the pure heuristic search to calculate the optimal solution. So this is a best way when we have like a huge graph to analyze, and we have the heuristic function information available, and if we have the memory constraint, then A plus will be a good algorithm to use. So here in the example, we will be seeing that each node has associated value on top within that square. So that means the heuristic value of the node, basically when we determine the heuristic value, it always has to be lesser than the actual cost. If it's estimated like greater than the actual cost, then this graph will not work. So we have to make sure on that. And then if we are starting from node 1, again, we can go to node 5 and 2. So associated cost calculation, I'll just quickly go through one node so we can understand how we do that. So node 2 will see the number 10 in this square. So that means the heuristic value for node 2 is 10, but it's not the total cost because the edge also have a weight, which is 2. So 10 plus 2 is 12. So that is the total cost to reach node 2. So if we go to node 5, then it has a 12 heuristic function value and 1 weight from the edge. So it will be 13. So when we go to the node 2, from node 2, we can go to node 3 and node 6. So again, we will be calculating the lowest cost here. So in this example, in node 3, we have 16, and then these two, we have to calculate these two edges because we are starting from the node 1. So same way we can follow till we go to the end of the end of the state, which is the goal state, and that time we will be omitting the highest cost path, and we will be choosing only the lowest cost path to drive down. And the last search algorithm we will be discussing today is the best first search. We also called it as a greedy search. This search implemented using the priority queues. The best first search is is a mix of both breadth first search and the depth first search. So we can call it as a combination of both. So we will be applying the heuristic function and calculating the estimate cost for each node when we are choosing the right path to reach to the destination. And since we discussed about the multiple different searching algorithms, so we will have to consider how to evaluate the performance of the algorithm. So there are four main components that will impact the performance of the algorithm, which is the complexity, time complexity, and space complexity, and optimicity and completeness. So from here onwards, I'll ask my friend to continue. Gira will take over from here. Thank you.
Thank you, Ayodhya. Now I'm going to discuss about the severe weather avoidance using informed heuristic search. Atmospheric process plays an important role in the navigation and guidance. Most of the airplane accidents is done in the air. Accidents involving aircraft account for 21.70% of the general accidents. During the year 1990, 25.9% of the air accidents are caused due to the weather. After the 1985 accidents at the Dallas-Fort Worth International Airport, the new guideline strategies were developed when the microburst came into contact with the plane. Another huge problem in the air is the thunderstorm weather problem. There are two ways to solve the thunderstorm weather problem. First way is to find the shortest route between the 2 points. Because of that, the areas of the severe weather can be avoided. The algorithm was created by Dijkstra, and it was used to make it easier to navigate through the bad weather. Though this method can figure out a safe route, it does not promise to give you a good one. The second way is by using the A star search. It has been used to figure out a new route that avoids a weather conflict caused by the thunderstorm on the original route. A heuristic function is used, and this function has the two parts. The first part gives the actual cost of moving from a starting point to the end point. The second part gives the estimation cost of the travel, and also it shows the new shortest route in the bad weather like thunderstorm. The bad weather can do a lot of severe damage to the plane. Updrafts and downdrafts make the pilot lose the control of the plane. Radar reflectivity, wind spread and direction, turbulence and temperature are all things that the pilot need to know in general. But the above figure shows how strong the thunderstorm is and its intensity. When making a radar image, a two-dimensional Gaussian function is used to give the intensity of weather at any point due to the thunderstorm. This table shows the intensity and weather information for different colors in the radar image. We want to avoid the yellow and red parts of the radar image because the intensity is greater than the 30 decibels. Plane can travel if the radar image shows none green and the blue colors because the intensity is less than the 30 decibels. To be clear, this weather data may not be 100% accurate. Thus, the radar data that is used as input can have some mistakes or it may not show the whole picture of the weather. And coming to the developing the weather avoidance algorithm constraints, the algorithm picks if the algorithm picks the flight path, it should be the shortest distance one that avoids the bad weather. There are three constraints in the weather avoidance algorithm: minimum segment length, maximum turning angle, minimum number of turns. The minimum segment length means between any 2 points on the flight path, the distance between them should be greater than or equal to the certain minimum distance. In order to make the pilot job easier, this is needed. Also, the plane should be able to finish one turn before starting another one. And the second constraint is the maximum turning angle. There should be no changes in the direction of the plane's flight path that go above 90 degrees. But this isn't always possible. When we write our algorithm, we limit the number of nodes that can be made from a single node. And the third constraint is the minimum number of turns. The flight path should be piecewise linear and the path should be as straight as possible. There should be as few turns as possible on the flight path. This will decrease the work of the pilot. And to create a map, grids are used. The distance between two consecutive nodes is determined by the grid size. The grid size can be greater than or equal to the grid size in the radar image. If the grid size of the map is greater than the intensity, it is set to the maximum intensity. And if the intensity is greater than the 25 decibels, then the map is inaccessible in that area. For the A star and SMA star algorithms, the changes are made in the memory requirements. In the SMA star algorithm, a specific space was left for the storage of nodes. There is a drawback in the SMA star search. If the amount of memory allocated is less than the amount needed for the best part to the goal node, this search strategy would either give a suboptimal answer or it would not give a solution at all. Thank you. Now, my friend Nanda will discuss about the results.
Hi everyone, and coming to the results, in the figures we have seen the four colors basically red, green and blue and yellow. It describes the weather condition. Based on it we can be able to start a flight, and one is the starting level and two is the ending level of a flight. And in this, blue determines the light weather type. It means flights can travel. In green, it shows the moderate. It means in our words, we can say it as a medium weather type. In this also, we can be able to travel. And compared to the other two colors, red and yellow, in this, better stop traveling because at any time we may get the risk at these colors. And next, coming to the figures. Yeah, coming to figure 5, it is shown that the red color, it means the intense weather type. Better avoid traveling at these times. It shows the corresponding inaccessible region. It means it is ready to choose another path because it is inaccessible. It is not allowing the flight at that position to travel. And in figure 6, it is showing that it is choosing the other another way using the algorithm. In figure 5, we have already seen that it is not possible at that position, so that to travel the another position in figure 6, it is showing the black line which determines the other way to go, to allow the plane to go. And in figure 7, the case 1 flight path with the radar image, it shows that the flight path with the radar image. In figure 4, we have observed already the same figure, but the difference between these two is we can see the algorithm, it means the black line. One is the starting position and two is the ending position of this. And on a runtime Pentium at 2 PC using the MATLAB, the algorithm takes 11.4 seconds to determine the safest and the shortest flight path in this case. So with this, in the case 1 is completed. So coming to the case 2, we can see what will happening there. And in the case 2, it is showing that as already said in the previous case, 1 is the starting point and the 2 in the ending point. The figure also depicts the thunderstorm flight path avoiding algorithm, and as we can see, it avoids thunderstorm activity intense in certain areas. The bare minimum segment length in this case is 8 units. That means it is 8 miles. On the radar picture itself, it is showing that, and the algorithm takes 15.25 seconds to complete and find the safest route of it. And coming to the figure 9, in case 3, a line of 3 stationary here. Compared to all the cases here, we will be using 3 thunderstorms in this, and the flight original path has been shown in the figure 9. In this, we can also see that the flight also lies, as that we can see in the figure clearly that the thunderstorms remaining compared to the remaining 2 cases, the thunderstorms are moving very fast in this one. And the underlying assumption as that shows both the airplane and the thunderstorms are moving at a constant but varying speed. Thunderstorm avoidance is used on occasion, and the algorithm generates a new heading for the airplane according to the current radar image. Then the aircraft then alters its course in accordance with the algorithm for avoiding thunderstorms. The interval of time difference between two consecutive heading changes is the smaller. The A is the algorithm's execution time, or B 10 seconds to compute the new heading, reading the time elapsed between the two consecutive headings. And regardless of the changes, the airplane maintains a constant velocity compared to the compared to the previous cases. It maintains a constant velocity. And coming to the figure 10 and figure 11, and the case 4, a line of 3 thunderstorms moving in the positive x direction, and in the case 5, a line of thunderstorms moving in the negative x directions. And figure 10 and 11 shows the simulation results for cases 4 and 5 respectively. The radar image is represented as a counter plot in the figures for clarity, and the grids are not shown. The area enclosed by the red counter has a greater intensity than 30 decibels. The area enclosed by the green counter has a greater intensity than 20 decibels, and the area enclosed by the blue counter has a greater intensity than 5 decibels. The dotted counters represent the intensity of thunderstorms when the airplane is at a starting point. 1. The solid counters represent the intensity of thunderstorms when the airplane has arrived at the terminal point. And coming to the point 2, as a result, the thunderstorm has moved from the area denoted by the dotted counters to the area denoted by the solid counters. In case 4, a line of 3 thunderstorms forms, moving at a speed of 40 miles per hour in the positive x direction each hour. The airplane is traveling at a constant speed of 150 knots from point 1 to 2. Figure 10 depicts the airplane's safe path in this case. And coming to the case 5, a line of thunderstorms is moving at 50 miles per hour in the negative x direction. In figure 11, one represents the starting point and the two represents the ending point. In every case, this is the common thing. One represents the starting point and the two represents the ending points. The actual safe path taken by the airplane is also depicted in the figure. The algorithm computes the safest and the shortest path as seen in cases 1 and 2 and 3 successfully between 2 points, and the amount of it takes a reasonable amount of the time. Furthermore, the individual in these cases, the segment lengths are less than for each of a minimum segment length is specified cases. The results of cases 4 and 5 show that the algorithm's effectiveness in the event of more thunderstorms. And coming to the acknowledge convergence and stability, and the set of rules was run on several other sample cases too. The set of rules, it means we can also say the algorithm as a set of rules, so that the set of rules does fail to give an answer in a collection of cases. It also fails to compute the safe detours if the starting point of the course lies within the location of excessive thunderstorm activity. The set of rules constantly attempts to discover the answer within side the head direction. So in occasion of being flanked by the thunderstorms along all the heading directions, the set of rules cannot retrace the course to get away from the thunderstorm, and it does not allow heating adjustments more than the maximum turning angle. Hence, it does not give satisfactory effects if the start line is simply too near the thunderstorm and if the thunderstorm extends extensively on each side. And coming to the conclusion, the consequences display that the algorithm successfully computes the safest and the shortest path in the sample place at a map. Also, the adjustments made in the A star seek technique ensure that the solution is reached in a short interval of time. Although these adjustments can endanger the optimality of the solution when specifically applied to the problem in hand, it isn't always an extreme issue, and the seek tree has finite intensity, and the intensity may be decided from the number of turns allowed in the flight path. The simulation consequences are encouraging as well, though better consequences may be ensured with the aid of using in addition tuning of the algorithm. Thank you.